Now let us see how U average depends on temperature. Dependence of U average on temperature we are discussing. So the average speed of gas molecule is given by the expression U average is equal to root over 8 RT by pi m. So here this is absolute temperature, this is a molar gas constant, this is constant pi, and this is a molar mass of the gas. Molar mass of the gas, that is capital M, is the mass of Avogadro number of molecules, and small m is the mass of single molecule. Now if you do cross multiplication, so here small m is equal to capital M by Na, and from this molar mass is equal to mass of single molecule into Avogadro's number. So in place of molar mass, you are writing mass of single molecule into Avogadro's number. Again here you have R in the numerator. Now you are going to get a Na in the denominator. R by Na can be replaced with the K, Boltzmann constant. So here this is gas constant per molecule, absolute temperature, mass of the gas molecule. Our requirement is how U average depends on temperature. You can see this is average speed of the gas molecule, and this is absolute temperature. So 8 K pi, mass of the molecule is also constant. All these terms are constant. As a result, we can conclude that U average is directly proportional to absolute temperature, root of absolute temperature of the gas. U average is directly proportional to root over T. So now let us take a collision number mathematical expression. Already the definition part we covered. So here collision number, this is the number of collisions made by single molecule in unit time and a unit volume. The definition already we discussed. And if n star is the number of molecules per unit volume, then a number of molecules within volume V. So here in volume V, how many gas molecules are present? So here you are finding, and from that obviously here n star is the number of molecules present in unit volume, but we are taking V volume. In V volume, number of gas molecules present will be n. Therefore number of collisions made by a single molecule with other molecules per unit volume, because in this volume n number of molecules are present. Therefore Z1, that is collision number, is equal to, so here volume of the gas into n star. So here volume of gas is nothing but we are taking volume of collision cylinder only, volume of collision cylinder. Already we expressed volume of collision cylinder is a pi sigma square relative velocity, and here relative velocity is root over 2 into U average. Therefore Z1 is equal to root 2 pi sigma square U average into n star. And if you see the terms, so here root 2 times of U average, that is relative velocity of the gas molecule, and this is collision diameter, or we can also say collision radius, and this is number of molecules present per unit volume. For example, if there is any hypothetical situation where only one gas molecule is moving, all other gas molecules are at rest, in that situation instead of taking relative velocity, you have to take just average velocity. That means you, in place of this relative velocity, you have to take just average velocity. Hence this root 2 term will not appear. Hence the equation will become like this. So this is the final equation you are getting here, but this is definitely hypothetical situation. This situation is practically not possible, because this is true only when one gas molecule moves and all other molecules are at rest. So here this is about a expression for collision number. Now let us see how this collision number depends on pressure and temperature. So just now we discussed the expression for collision number, that is Z1, that is equal to volume of collision cylinder into effective number of molecules, that is number of molecules present per unit volume. So here in this expression, root 2 is constant, pi is constant, sigma collision diameter is also constant. Now let us expand U average and N star. So here U average and N star, you already know U average is directly proportional to root over absolute temperature, and N star is equal to P by KT. And finally, in place of U average and N star, if you substitute these terms, you will be getting Z1 is directly proportional to root over absolute temperature into P by T. And if you go for further simplification, you will be getting Z1 is directly proportional to pressure and inversely proportional to root over absolute temperature. And you have to take three cases. In that, the first case, if pressure is constant, if pressure is constant, so here this is constant, then Z1 is inversely proportional to root over absolute temperature. In isobaric conditions, you can apply Z1 is inversely proportional to root over absolute temperature. If temperature is constant, if temperature is constant, in this expression, if temperature is taken constant, Z1 is directly proportional to pressure. So this is the expression you are going to get. Temperature is constant, therefore it is isothermal condition. And the next one, if volume is kept constant, if volume is kept constant, here we have to use Gay-Lussac's law. According to Gay-Lussac's law, at a constant volume, pressure is directly proportional to absolute temperature. Based on this, in this expression, in place of P, I am going to write T. In place of P, I'm going to write T, because pressure is directly proportional to temperature. And here already in the denominator we have root over T, therefore Z1 is directly proportional to root over absolute temperature. In place of temperature we can also write the P, because it is only ratio, hence Z1 is directly proportional to root over pressure. So this is about dependence of Z1 on pressure and temperature.